Hi! In this video, we will consider the problem to find the minimum number of refills during a long journey by car. You will see the similarities between this problem and the largest number problem from the previous video. By the end, you will be able to describe how greedy algorithms work in general and define what is a safe move and a subproblem. Consider the following problem. You have a car such that if you fill it up to full tank, you can travel with it up to 400 kilometers without refilling it. And you need to get from point A to point B, and the distance between them is 950 kilometers. Of course, you need to refill on your way, and luckily there are a few gas stations on your way from A to B. These are denoted by blue circles, and the numbers above them mean the distance from A to the corresponding gas station along the way from A to B. And you need to find the minimum number of refills to get from A to B. One example of such route is to get from point A to the first gas station, 200 kilometers, then to get from first station to the third gas station, 350 kilometers distance, then from third gas station to the fourth gas station, 200 kilometers, and then from the fourth gas station to B, 200 kilometers. But that's not optimal, we can do better. Here is another route which only uses 2 refills. We get from A to the second gas station, less than 400 kilometers. Then we get from the second gas station to the fourth gas station, again less than 400 kilometers. And then from the fourth gas station to B, only 200 kilometers. And this route uses only 2 refills. And it turns out that in this problem, the minimum number of refills is exactly 2. More formally, we have the following problem. As the input, we have a car which can travel at most L kilometers, where L is a parameter, if it's filled up to full tank. We have a source and destination, A and B, and we have N gas station at distances from x1 to xn in kilometers from A along the path from A to B. And we need to output the minimum number of refills to get from A to B, not counting the initial refill at A. We want to solve this problem using a greedy strategy. And greedy strategy in general is very easy. You first make some greedy choice, then you reduce your problem to a smaller subproblem, and then you iterate until there are no problems left. There are a few different ways to make a greedy choice in this particular problem. For example, you can always refill at the closest gas station to you. Another way is to refill at the farthest reachable gas station, and by reachable I mean that you can get from your current position to this gas station without refills. Another way is, for example, to go until there is no fuel and then just hope that there will be a gas station in the end. So what do you think is the correct strategy in this problem? And of course the third option is obviously wrong. The first option is also wrong if you think about it, but the second option is actually correct. It will give you the optimal number of refills. We'll prove it later. For now, let's define our greedy algorithm as the whole algorithm. So we start at A and we need to get to B with the minimum number of refills. We go from A to the farthest reachable gas station G, so that we can get from A to G with full tank without any refills in the middle. And now we try to reduce this problem to a similar problem. We make G the new A, and now our problem is to get from the new A to B, again with the minimum number of refills. And by definition, a subproblem is a similar problem of smaller size. One example of subproblem is from the previous video. When we need to construct the largest number out of a list of digits, we first put the largest digits in front, and then we reduce our problem to the problem of building the largest number out of the digits which are left. In this problem, to find the minimum number of refills on the way from A to B, we first refill at the farthest reachable gas station G, and then solve a similar problem, which is a subproblem, to get from G to B with the minimum number of refills. Another important term is safe move. We call a greedy choice a safe move if it is consistent with some optimal solution. In other words, if there exists some optimal solution in which first move is this greedy choice, then this greedy choice is called a safe move. And we will prove a lemma that to refill at the farthest reachable gas station is a safe move. Let us first prove it visually. Let's consider some optimal route from A to B and let the first stop on this route to refill be at point G1, and let G be the farthest gas station reachable from A. If G1 and G coincide, then our lemma is proved already. Otherwise, G1 has to be closer to A than G, because G is the farthest reachable from A and G1 is reachable from A. Now let's consider the next stop on the optimal route and let it be G2. And the first case is that G is closer to A than G2. Then the route can look like this. In this case, we can actually refill at G instead of G1. And then we will have another optimal route, because it has the same number of refills, and G is reachable from A, and G2 is actually reachable from G, because it was reachable from G1, but G is closer to G2 than G1. So this is a correct route, and in this case our lemma is proved. And the second case is when G2 is actually closer to A than G. And then the route can look like this. But in this case we can avoid refilling at G1 at all and refill at G2 or even refill at G in the first place. And then we'll reduce the number of refills of our optimal route, which is impossible. So this second case actually contradicts our statement that we were looking at an optimal route. And we've proved our lemma. To recap, we consider the optimal route R with the minimum number of refills. We denote by G1 the position of the first refill in R, and by G2 the next stop is R, which is either a refill or the destination B. And by G we denote the farthest refill reachable from A. And we consider two cases. In the first case, if G is closer than G2 to A, we can refill at G instead of G1, and it means that refill at G is a safe move. Otherwise, we can avoid refill at G1, so this case contradicts that the route R is the route with the minimum number of refills, so there is no such case. And we proved our lemma. And in the next lecture, we will implement this algorithm in pseudocode and analyze its running time.